Welcome to this explainer. Okay, be honest. Have you ever stared at the periodic table and just felt completely overwhelmed by all those letters and numbers? I know I have. But what if I told you it's not actually some daunting chart you have to rigidly memorize? No, it is literally the universe's ultimate cheat sheet. Once you figure out how to read it, it completely unlocks the secrets of how everything around us interacts. So let's get into it.
All right, let's dive right in and look at the master map. Try to think of this not as just a random list of elements, but as a highly structured city grid. Every single element has an exact specific address, and that address isn't arbitrary at all. It's strictly driven by the element's hidden inner workings. By the end of our time together today, you won't just be staring at little boxes. You'll actually be reading the fundamental laws of chemistry.
Here is our roadmap for today. We'll be covering the periodic map, decoding periods and groups, the electron configuration code, and finally, the atomic radius trend.
Okay, part 1, the periodic map, where we establish the grid.
So the entire foundation of this map rests on what's called the modern periodic law. This is basically the principle that elements are classified and arranged by increasing atomic numbers, which then form specific rows and columns. Now, historically, early chemists like Mendeleev tried to organize elements by their atomic mass, but honestly, that led to some pretty messy discrepancies. The real game changer happened when scientists ditched atomic mass and shifted the focus entirely to atomic numbers. That one single shift, it made absolutely everything fall perfectly into place.
Moving right along to Section 2, decoding periods and groups at the micro level.
Now, the core rule of our grid is actually super simple. Periods are the horizontal rows numbered 1 through 7, and the rule here is that elements in the same period have the exact same number of electron shells. On the flip side, we have groups, which are the vertical columns. Elements in the same group share the exact same number of outermost or valence electrons. Because of this shared number, elements in the same group behave very similarly when it comes to chemical reactions. It's like they're in the same chemical family.
So the absolutely crucial point here is that a period's length isn't just random. As you can see, the period number corresponds exactly to the number of shells. This dictates how many orbitals are occupied, and therefore how many elements can physically fit in that specific row. Take period 1, for example. It only has 2 elements, hydrogen and helium, because it only occupies the 1s orbital. Periods 2 and 3, they fit 8 elements. And by the time we hit period 4, we're occupying the 4s, 3d, and 4p orbitals, which expands the row to fit 18 elements. Pretty cool, right?
All right, Section 3, the electron configuration code. Let's crack the code to find that address.
The fundamental rule to remember here is that nature is, well, kind of lazy. Electrons really don't want to expend any more energy than they absolutely have to. They always tend to seek out the lowest possible energy state, which we call the ground state electron configuration. And because atoms of different elements have different numbers of electrons, each element gets a completely distinct, unique electronic configuration. It's essentially the atomic fingerprint that tells us exactly where an element belongs on our map.
Let's see how this actually works with a highly practical exam secret. We're going to find chlorine's address together. Okay, step 1, identify its atomic number, which is 17. Step 2, write out its ground state configuration, filling the orbitals from the lowest energy up. So that gives us 1s, 2, 2s, 2, 2p6, 3s2, and 3p5. Now, for the final step, just look at the outermost shell, the third shell. It has 2 electrons in the s orbital and 5 in the p orbital, giving us a total of 7 valence electrons. Boom! Those 7 valence electrons immediately and definitively reveal chlorine's home, group 7a, a main group element. Honestly, it's exactly like reading GPS coordinates.
Which brings us to Section 4, the atomic radius trend. Let's look at the physics of the table.
Now take a close look at the green spheres representing the atomic radius. Notice how they actually shrink as you read from left to right across a single period? Like, look at the jump from lithium over to neon. But when you look from top to bottom down a vertical group, say from lithium down to cesium, the spheres get steadily larger. So the atomic radius varies periodically based purely on an atom's position in the grid.
And this brings us to a classic paradox. I guarantee you're going to face this on your exams. Why on earth would adding more protons and more electrons across a period make the atom physically smaller? I mean, common sense might tell you that adding more stuff to an atom should make it bigger, right? But as we just saw, moving to the right across a period actually shrinks the atomic radius. Let's break down why.
The answer actually lies in an invisible tug-of-war happening inside the atom.
Remember, radius largely depends on the strength of the attraction between the nucleus and those outer shell electrons. As you move to the right across a period, you're adding electrons to the very same shell, but crucially, you are also adding more protons to the nucleus. This growing positive charge in the nucleus increases what we call the effective nuclear charge. It basically acts like a super strong magnet, exerting a much stronger attraction and tightly pulling those outer shell electrons inward. More pull literally equals a smaller overall radius.
Conversely, let's look at what happens when you move down a vertical group. As you go down, say from sodium down to potassium, you are introducing entirely new electron shells, because orbital size inherently increases with the increasing principal quantum number, which we designate with the letter n. The size of the atom physically expands, so even though the nuclear charge is still increasing as you move down the group, the addition of those completely new, larger shells completely outweighs that inward pull, and that is what makes the atom larger.
Ultimately, what this all means is that you don't need to stubbornly memorize the periodic table. You really just need to understand its underlying logic. The atomic number dictates the electron configuration, which dictates the period and group, which in turn perfectly predicts physical properties like atomic radius and chemical behavior. It is a beautifully interconnected system. Which leaves us with a final, fascinating thought to ponder. If you know an atom's electrons, do you hold the blueprint to its entire destiny?